So we're going to go over the integrated rate law for a first order reaction, and that is some reaction where it kind of looks like this. A goes to products, and remember the equation doesn't tell us what the order is. We do that experimentally. We know that the rate law looks like this: rate equals some constant K times the concentration of A. So this is the rate at which it changes, and that's still the other part of the rate law. If you use a little bit of calculus, you can get at an expression that looks like this, where the natural log of A at some time t is equal to negative K, the rate constant, times t, plus natural log of the original concentration of A. And that is a y equals mx plus b slope-intercept form of a line. And so if this were to be plotted, natural log of A on this side and time on this side, we would see some sort of line that slopes downwards like this. Okay, so that is the integrated rate law, and the really nice thing this does is this puts concentration and time in a relationship with each other, so we could predict how much of something might be left after a certain amount of time has passed. Now, one important thing for us to look at is the half-life, and that is the amount of time it takes for the concentration to go down by a half. So if A naught is our original concentration, then AT is our concentration at some time t, and that is defined as the half-life when this concentration AT is equal to half of what we started with. Okay, so half of it has gone away, or half of it is reacted. So if we substitute this in, our expression now becomes this, A naught over T over 2, and that's equal to negative KT1 half plus natural log of A naught. All right, I can subtract natural log of A naught from both sides. So natural log of A naught over 2 minus natural log of A naught equals negative KT to the 1 half. I can expand this expression out using the the rule of logs. So A naught over 2 is actually natural log of A naught minus natural log of 2 minus natural log of A naught again, because that's what's already there, equals negative KT1 half. These cancel out, and what I'm going to end up being left with is this expression, natural log of 2, and if you evaluate that, because that's just a number, 0.693 is what you get, and that's equal to there's a negative there, so those two, this and this, end up becoming positive. So KT to the 1 half. Okay, so now we have a number, and if we know the half-life, then we can get the rate constant, or if we know the rate constant, we can get the half-life, just with that number right there. So it's a relatively handy thing. Finally, what we're going to look at is an example problem. So we've got this cyclopropane, and it is in equilibrium with this propene. So what we're going to do is we're going to just try and answer this question. So we've got a rate constant of this at 720 K. Now all rate constants are temperature dependent. The initial concentration is this, and what is the concentration after 235 minutes? Notice our rate constant is in per seconds and this is in minutes, so we're going to have to convert this number of minutes to, I believe it is 14100, basically multiplying this number by 60 to get to seconds. Okay, so let's go through and see if we can just solve this. So the natural log of A at some time t is equal to negative 3.36 times 10 to the minus 5 per second. And that is going to be multiplied by this number of seconds, 14100 seconds, plus the natural log of our initial concentration, 0.0445. Okay, now the nice part about this is that this entire side is just all numbers. And so if I go through and put that in my calculator and solve, I would end up getting negative 3.586 is my natural log of AT. And you might remember from our previous work, the way we have to solve this is we have to raise both sides to the e Euler's number. So e raised to the negative 3.586, that comes out to 0.0277 molar. And that should make sense, meaning that the concentration I have after this number of seconds have passed is lower than the concentration that I started with. Okay, and it's lower by a number that, not quite half seems to make sense. This is not quite the half-life for this one. So that's great. The integrated rate law is, you can reduce it to a plug and chug, but what it really is, it's a wonderful relationship between concentration and time for first-order reactions.